Hey everybody, I'm Molly McKinney with NASA 360 coming to you live from NASA's Langley Research Center. As you can see, we are in the historic hangar here at Langley Research Center, and we are covering one of my favorite competitions of the year. This is the second year in a row that we've covered the Rascal Mars Ice Challenge. And though it may not look like the surface of Mars behind me, we have teams that have gathered from across the country to compete in this really exciting challenge as we simulate the surface of Mars. And let me give you a quick little tour of the pit area really quick. Teams are using harvesting systems to try and collect ice and eventually water from large ice deposits like we found on the subsurface of Mars. And let's make it as difficult as possible for our camera operator as we have him walk up these stairs. But this is going to be a really nice vantage point to introduce you to this challenge and what teams are tasked with doing. Most teams have used a design that's similar to this one, where you can see this auger drilling system. Teams have to drill through this subterranean simulated Martian soil. Are we on your way? We can move if we are. And underneath this soil are these large ice deposits like we found on the subsurface of Mars. So some of the teams are extracting water right from this collection bin. They're using some kind of heat-based technology, and they're able to extract water right from there. Other teams are collecting ice chips or ice samples, and then they're melting ice in different bins outside of the unit. Some are either even transferring this into vapor, and then they're recondensing into water after that. And so the perfect person to talk to about the Mars Ice Challenge, brought to you by Rascal, is right over here. Chris, you're the perfect person to give us an overview. And this is great because you can actually see all the teams that have traveled here to compete. If you're joining us just now, this is our NASA 360 coverage of the Rascal Mars Ice Challenge. Teams have gathered from universities all over the country to come here and compete. So give us an overview of this challenge for folks that just joined us and why it's important.
So the goal of the challenge here is to get experience with how would you acquire water from subsurface ice on the surface of Mars. Because if we're going to do a mission to Mars, or a mission to the moon for that matter, we're going to need a lot of water in order to do it. And what these students are doing today is testing some of the potential technologies and systems that we might use to do it. So as you can see from the list here, we've got teams from all over the country that have come in. They're here with different ways to try and drill the ice, or lift it with an auger, or melt it in the hole and then pump it out. And the goal here is to see, can they deliver clean water to us in a way that we could someday translate to using on Mars.
How are the requirements that they're tasked with here similar to real Mars and NASA missions that our scientists are performing today?
So we tried to build a simulated test station for them that gave them a chance to try something that's like the Martian environment. They've got to first go through about 18 inches of regolith, or essentially dirt mixed with some rocks here and there, before they strike ice. This is something we think we might find, especially in the higher latitudes on Mars, where there might be glaciers just a few meters below the ground. Once they drill through that dirt, they then will encounter the ice, and it's up to them to figure out how they either melt it there or lift it up as ice, bring it out, and convert it into the clean water they have to collect in order to do well in the competition. But then we're also asking them to tell us about how they would change their system to operate on Mars.
And why is that important? What are the different conditions that they might encounter on Mars that they're not necessarily encountering here on Earth?
So Mars brings a number of challenges with it. It's usually a lot colder there than it is here on Earth, but even more important, there's a lot less atmosphere. Only about 1% as much atmosphere on Mars as there is here on Earth. So that means as soon as they expose the ice to the open, not air, it starts to turn into a vapor, which means they would potentially lose anything they acquire unless they design their system to deal with that. It's not a problem they have to deal with here, but if they're going to do their system on Mars, and we asked them to talk about this in some of the other papers they wrote talking about their system, they have to figure out how they're going to deal with the challenges of the Martian environment with the system here adapted for that other destination.
That's fascinating. And I guess it would be a clean sample if it's turning to vapor, so that's one less thing they have to worry about here.
Absolutely. A couple of the teams have even talked about using that very principle called sublimation in their design for Mars. They would essentially turn it directly into a vapor. That would get rid of pretty much anything they'd be worried about contaminating it, and then they would condense it back into liquid water to use. It's just an approach that you've got to make sure you're capturing that vapor back into water for yourself and not letting it just drift off onto Mars.
water is crucial for humans to be able to survive and work in deep space. What other, beyond just clean drinking water and personal hygiene, what are some of the other uses that water might provide for deep space exploration?
So whether it's on the moon or on Mars, one of the best things we can do with water is actually manufacture the rocket propellant, the fuel and the oxidizer that the crews would use to come home. Right now, because of how difficult it is to send any amount of mass either to the moon or Mars or anywhere off of Earth, we want to minimize as much mass as we can that we have to send there and instead get mass there. And in this case, getting water, it gives us that clean drinking water, it gives us that water for hygiene, but we could also use it to make the fuel to bring them home. We could also use it to make plastics that they could someday use, or we could use it to run a greenhouse to make food for them in the future. So it's really a valuable resource in a number of different applications for what they're going to do at that new destination.
So this isn't just a fun challenge that someone thought up. This is a real world opportunity for them to collaborate with NASA scientists and try and solve some real world problems.
Absolutely. The ideas here, we've got judges in the competition from all across NASA. We have judges from industry. We have a lot of folks here who are looking at these ideas and saying, how do we then take this idea that a student team has come up with and adapt it in order to use it at Mars? So we're taking advantage of the fact that these teams are able to test some of these ideas for us, and then we're going to turn around and use those to solve the very real challenges that we would encounter when we go to Mars, when we're on the moon, when we're trying to have human beings out there elsewhere in the solar system.
That's great. Thank you so much. It's been so nice talking to you, Chris. I appreciate it.
Sure thing.
For folks that are just now joining us, we're bringing you live coverage of the Rascal Mars Ice Challenge. Teams are tasked with trying to harvest water from ice deposits that are buried under simulated Martian regolith or simulated Martian soil. So we're going to go talk to some of the teams now. We just heard from Chris, who's a NASA expert, on why challenges like this are important. So let's learn really quick from some of these teams. You can look at all the different drilling systems as we walk around the pit area and kind of compare the differences between them. And let me see if I can pull Caroline out real quick. She's talking to someone else. Let's see if we can grab her. Caroline, can I grab you real quick? I'm so sorry to interrupt you. It's hard. She's such a great person to talk to. Everybody wants to talk to her. So, Caroline, can you tell us a little bit about your drilling system and how it's different than some of the other ones and why it's important?
Yeah, sure. So our drilling system, we're using a core drill to drill for the ice. And a core drill essentially is a cylinder that will dig into the dirt and cut right into the ice and then extract cylinders of ice. So core.
We're actually taking core samples of ice.
Taking core samples of ice on a large enough scale that we're going to be able to produce a good amount of liquid water with each core. And then something that we think is a little bit unique is our method of water purification is thermal distillation. So it's a lot more regenerable than other types of filters because you don't have to replace any sort of mesh or any sort of ones that builds up with different types of contaminants. So thermal distillation is just the vaporization and then recondensation of water. And
it sounds like this is a process that would happen naturally on Mars, so you wouldn't have to change that technology too much for it to apply there.
Yeah, definitely. I mean, so the low atmosphere and then cooler temperature on Mars actually allows you easier sublimation than on Earth. So the actual vaporization is not going to be a problem. The issue really comes into play with the recondensation, just because with a low atmosphere, it's challenging to generate enough pressure for any sort of blower or compressor or vacuum that you would need to condense it. That being said, it is being done on the rovers. There's different types of vacuum systems that are used for mass spectrometry and other different types of things. So we are actually using a heat exchanger as our method of recondensation. So we have a copper coil up in the galvanized steel pipe there.
Let's get a little closer. I want to see it.
Yeah, so we have a copper coil that goes up through into this pipe, and then we are using very high-speed air to recondense the water. So that was something that we determined the size of the heat exchanger that we would need for the core size. In terms of the actual vaporization though, because Earth doesn't have as low of an atmosphere as Mars, we actually use an induction heater to vaporize it. So it's a very energy efficient process. Essentially we run a current around a steel pipe which induces a current through the pipe, and we're actually able to heat up that 2 to 3 degrees per second. So in about 3 minutes, we can vaporize our entire core. Oh, I told you this before. So this, the pump we're using to blow air actually is used to blow up bounce houses. We were really trying to find something that was going to reach the CFM that we required that wasn't going to exceed our weight requirements and our energy constraints. Sure. So we actually get 670 CFM with our air pump. Yeah, it's a fun color too. So.
It is a very fun color, very festive. What do you think has been the biggest obstacle you've run into with this challenge? What's been the hardest thing to overcome?
I think a really challenging part has been the communication between our control system and the different components of our drill. It's definitely been a lot of iterations of this prototype, so we've been making our control systems have to change up their code a lot. And kind of like coming together and being able to put all of the different components to interact with each other properly and to work at the specifications that we want is something that has definitely been.
I can imagine. That would be very difficult. Well, thank you so much. I know you have plenty of people to talk to other than me, so thank you for your time. I appreciate it. If you're just now joining us, this is NASA 360's coverage of the Rascal Mars Ice Challenge. And the challenge today consists of two main components. The first is design, and the second is demonstration. So teams are forced, that's a harsh word. Teams are tasked with the challenge of designing an ice and water harvesting system for use on the surface of Mars. And the second part of this is developing a technology demonstration of the Martian system, but it has to be modified for Earth-based analogs, obviously. So the atmosphere and gravitational pull on Mars and Earth are very different. So building a system for Mars that we can test here on Earth is no easy task. That's part of what makes the Mars Ice Challenge so challenging. And what's fascinating to me as somebody who gets the opportunity to cover this is that each team brings really different ideas to the table. All of those, different ideas, that diversity helps expand our collective understanding, not just for ourselves, but for our country, our solar system, our universe. And so today is day one for these teams. They are allowed to physically work and touch these systems that they've designed. Day two is a little more difficult. The systems don't have to be autonomous, but they are not able to be hands-on with their machines. So something breaks, they can't fix it. And so in just a second, we're going to talk to Tanner over at the School of Mines when you all are ready. They really are doing real work. I'm pulling them away from actual work. This isn't staged. So Tanner, give me just an idea of your drilling system, how it's different from some of the other teams, why you chose to design the way that you did.
Yeah, so our team came last year, and our main thing we wanted to do was be different than last year's team. They had some major problems with just running one auger. So what we decided to do was include an auger, but also go to a heat probe, which we'll use to melt the ice down in the hole and then extract the water through that.
Is that difficult to get a clean sample with yeah?
Yes. Easy answer. Very, very difficult. We have only a little bit of mud, it seems like. So yeah, it's very hard. We seem to be getting a lot of clogging. What we've found to be the hardest part is filtering the water right at the hole, because it's very muddy, it's very mucky. And
is that different than what you practiced with in Colorado?
Yes and no. It's mainly we found to be the hard part, the life. We never tested this for 4 hours, which we've been running at now. So trying to figure out that life, just a cycle of everything, is very challenging. So that's been the hardest part for us, because it worked great initially right off the bat, which we kind of knew because those are the tests we ran. But now getting into the 4-hour marks, things are kind of falling apart. But we're getting there.
What is your background in, and what are some of the different backgrounds from your team members?
Everyone on the team is actually all mechanical engineers. So we're all seniors who graduated actually in May. So this is our last little hurrah before we're off in the real world. But yeah, we're all mechanical engineers. There's a couple of us. One has a minor in electrical and one has a minor in comp sci.
That's helpful in settings like this.
Yeah, they unfortunately couldn't be here now, so we all had to have a crash course in electronics and comp sci, but it's been all right. I think mechanical has really helped us. I think that's probably one of the more stronger backgrounds, because so much of this is working with robots. So it's been really helpful.
What are they doing right now?
Right now, we are in the middle of another melting run with our heat probe. So we're currently trying to get another batch of water out. What we've been struggling with probably the last 30 minutes is clearing out our vacuum tube that runs through the center of the heat probe.
It's getting clogged with soil.
Yeah. And it's really, really long. It runs the entire length, so down into the blue bucket and all the way up. And also, we can't really pull it out and switch it out because that requires us taking apart the whole thing. So we're kind of stuck.
It's frowned upon. Shoot. I'll let you get back to it. I hope you can fix it.
Thank you.
I really do. I think you will. I have faith. If you guys want to head over this way, we have one more team to talk to this afternoon. And that's what's so difficult about challenges like this one, especially for School of Mines. They're based in Colorado. They have to, test this system. It usually performs great in their condition on campus. And then they have to break the whole thing down, travel it here, reassemble it, and something always doesn't want to play nicely. Hey, nice to meet you. I'm Molly. George. So tell me a little bit about your team, where you all are from, and your design.
So we are from Rowan University, which is in South Jersey. This is the Dr. Seuss, which stands for Drill-Based Retractable Extraction and Unified Separation System. It's a bit of a tongue twister.
That is. I'm glad you said that, line, and not me.
So we have a few novel concepts here. One thing I'm really proud of, if you want to walk over here, I can show you.
I would love to not stand so far away.
There's some cool stuff we got going here. Our whole thing, the goal here was efficiency. That's what we cared about, because that's what's important on Mars. The more efficient you are, the more you can extract, in essence, because you can build a bigger, better system using the same amount of power. One of the ways we did that was using conduction versus convection in our heating, which, to spare all of the boring details, we did a lot of simulations and found that it was better to keep in constant contact with the ice when we were melting it than to just have something warm in the center and let the heat disseminate out. So what we have here is this umbrella mechanism that I designed that as the ice melts underground, this opens up. So it keeps constant contact with the ice. So we get that conduction. On top of that, we have rotation here that goes back and forth, so we can do a complete 360 circle underground. So we don't have to drill a bunch of holes like a lot of other concepts do. So even with elements this short, these are, compared to what we could put on Mars, these are extremely short. We get about 20, 30 times more water than if we just bored a straight hole. And if we put these to, say, 20 inches, 25 inches, we'd see 200 or 300 times more water. So we save all of that time and energy that's wasted with drilling a whole bunch of holes. So that's our big, I think, claim to fame with this system. That's the thing I'm the most...
That's the big differentiator.
Yeah, we have a few other cool things that help drive that as well, because there's a lot of concerns with Mars about what if something goes wrong. So, for example...
You can't just fix it like you would be able to in this setting.
Exactly. So let's say we're doing it and we miscalculated how strong the ice was, and everything just collapses. With a lot of systems that come out like this, you would think, oh, it's just going to break. But that's not the case with us. We have something called a slipper clutch, which is used a lot in RC cars. We are able to adapt it to this system. So even if the motor is still trying to push it out, if this is open and overburden or dirt or ice, something heavy falls on it, despite the motor trying to spin it the other way, it will still come back to center and it will survive.
That's really impressive. And so tomorrow, day 2, the design doesn't have to be autonomous, but you have to be completely hands-off. Do you anticipate any challenges with that?
We didn't originally anticipate challenges with that. We have all...
No one does originally.
However, if you look at it, you can see we still haven't broken ice or broken through the dirt just because of an electrical issue we're having. We feel like we might be able to fix it. If not, we might just run some stuff manually to at least show what we can do, even if we don't get points for it. Because this is all about exploring new concepts. So it's okay if we lose. We just want to show what we can do.
Everyone's a winner today and tomorrow. Thank you so much, George. It was nice meeting you. Good luck with your system. I think it'll be fine for tomorrow. If you're just now joining us, this is NASA 360's coverage of the Rascal Mars Ice Challenge, and we're talking about deep space resources and how vital they're going to be for us to have any hope of exploring Mars one day, doing continued exploration of the moon. All of these are really, really important for us. Obviously, part of exploring the solar system will be living off the resources wherever we go, and this is known as in situ resource utilization. It's becoming increasingly important the farther we travel from our home planet. So the less dependent our astronauts can be on Earth-based materials, the deeper we can go into our solar system and hopefully beyond one day. So the perfect person to talk with us about that is Jerry. Let's head right over here. This will be a great spot. Look at this, NASA's journey to Mars. It's the perfect backdrop. There we go. So, Jerry, we're talking a lot about in situ resource utilization and how important that is for our astronauts to hopefully go into deep space and explore Mars and explore some of these other planets. So if you can talk a little bit about why this is a mission for NASA and why it's so important.
Well, what we've learned is if we're going to explore space, especially with humans, and do it for a long period of time, you can't take everything from Earth. And there's what's called a gear ratio. So for every kilogram of material you land on the moon or Mars, takes something on the order of 7.5 to 10 kilograms has to be launched into Earth orbit. So if I need to make propellants or have propellants to get off of, for my rocket ship, to get the astronauts off of Mars back into orbit.
A return ticket.
A return ticket, which they definitely want.
They would appreciate.
It takes about 30 metric tons of propellant to do that. Multiply that by 7.5 to 10 or 11, and we're talking 2, 3 heavy lift launch vehicles just to deliver the propellant to Mars.
That's costly.
Lots of money, risky. Every time you have a launch, you have to integrate it, you have to send it, there's a risk associated with it, it has to land on the surface. So to a certain extent, we're not helping astronauts get to Mars. We're helping astronauts stay on Mars and get home.
Which may be more important. I think if you ask their families, they would probably say that's true. Yes. So why are challenges like this one important in that whole mission?
Well, one of the things that happens is there's always great ideas out there. And NASA itself can only focus on a few of them, with their engineers. A challenge like this allows universities to come up with great ideas, try different techniques, and we get to benefit from seeing what works, what doesn't, maybe help tweak their designs or take some of those designs and work with them and others to perfect them. So it's definitely a way of opening up the opportunities, letting new ideas, new thoughts, and definitely develop students that one day could work for NASA or companies that help us get to Mars.
Sure. For folks that are just now joining us, this is NASA 360's coverage of the Rascal Mars Ice Challenge, and teams have been tasked with the difficult challenge of extracting water from ice deposits buried under this subterranean Martian regolith. And so why is water one of the most crucial resources for us to learn how to harvest for deep space exploration?
Well, it's one of those things that has so many useful applications. And besides drinking it and cleaning your clothes, you can actually divide or break down water into its atoms, the constituents, oxygen and hydrogen. Oxygen can be used for breathing, but oxygen and hydrogen are great propellants for rocket engines, fuel cell power systems, and such. And, with hydrogen, you can actually, and carbon dioxide, you can actually start a whole chemical production industry. The most simple of which is methane, which is a really good fuel. But you can start making plastics and other products. So now you start thinking about additive manufacturing and how I can start using those techniques. So water is also a great radiation shield. So instead of taking everything from Earth, you have a water wall around your habitat where the astronauts are. It saves them, cuts down on the radiation. It's a nice water supply for drinking under different circumstances. And you may start thinking about food growth. Even things like animals and fish require some level of water. So it really has so many useful benefits. And then going back to the fact that if you had to carry all your water from Earth, that becomes
Again,
difficult.
costly, lots of weight.
So anyway, that's besides, there are a few resources that we really look for. Water, if we can find it anywhere in the universe or wherever we're going, is one of the number one resources. Forms of oxygen are second, because again, we can use oxygen for breathing. It also, typically for chemical propulsion systems and rockets, about 75 to 80% of their mass is oxygen. So even just oxygen alone is fantastic.
And so one more time, why are competitions like this so important for NASA and for experts? And just because we have guests that are joining us, for a little 2-minute span. So I just want to make sure everyone understands.
Okay. Well, here again, I think competitions form many different reasons. For us, it allows us to examine a whole bunch of different ideas very cheaply. Great ideas, whether they work or not. The next is developing our next generation of engineers, whether they work for NASA, an aerospace company, or something else. Being able to do these things really is important. The challenges, again, for the universities are fantastic because it's like real world. They have to deal with procurement. They have to deal with budgets. They have to deal with technical issues.
To submit con-ops.
And everything. And so my son has just finished his own degree in aerospace engineering and was lucky enough to...
Did he have a say in that, or did you just tell him that's what he was going to do?
I had tried to convince him not to go into aerospace engineering, but I guess I was too bad or too good of a role model, one of the two. But it's these kind of things that really shape an engineer, and again...
These are so important. I mean, these discoveries in aeronautics and space exploration and science and technology aren't just transforming our understanding of ourselves, but it's our understanding of our planet and our solar system and our universe.
Yes. And these type of things, again, if we can mine water on Mars, it opens up a tremendous possibility for how we can stay there for long periods of time. Elon Musk and others have these ideas that we need to get off planet for the survival of our species to a certain extent. And without a water resource like this, you can't sustain.
Not feasible.
Something like that.
Yeah. Well, thank you so much,
No
Jerry.
problem.
It's great talking to you. And competitions like the Rascal Mars Ice Challenge really help us push technological boundaries and inspire the next generation, some of whom you're seeing on the floor right here today. I mean, just imagine what these researchers of tomorrow are going to be able to accomplish as they make that next giant leap forward for humankind. So I wish we had more time. We're going to be covering this challenge tomorrow as well, so make sure you stay tuned for that. On behalf of NASA 360, I'm Molly McKinney. If you'd like to learn more about what your space agency is doing, please feel free to follow us online at nasa.gov/NASA360. We're also on social media, on Facebook, on Twitter, and our new Snapchat, which we just opened today. And we'll see you next time. Thank you all so much for being with us. Bye.